Very nice to be here. It's delightful to be here in this new setting. As I was saying to Professor Leibovitch, we wanted to try this in a new format for us. I'm Andrea Bartoli, I'm the Drusi French Cambi Chair here at ICAR. I'm going to be the new director in July. And we became aware that the way ICAR interacts with the world could be enhanced tremendously by use of very old-fashioned conversations and very modern technology that makes available this conversation to an audience that would have our time being here physically. So welcome to everybody who is here. Maybe we can go around the room to just give a sense of who is who. But we will have a seminar today that is experimental for us, in a sense that we would like to think this in a way as a beginning. It's the first time that we're using this format, a conversational format in which the lecture or the presenter is embedded into a conversational space and is ready to be edited in such a way that will be used on the web somehow, somewhere, ready to be of help if anybody thinks that what we have, what we're going to share is meaningful. So why don't we go around? That will be the first moment of the afternoon. Then I will ask a few questions to Professor Leibovitch about him and how he got involved in this kind of research and how this research is framed within his own interest. Then we will hear the lecture, and then we will have further time to discuss and so on. I asked permission to Professor Leibovitch to invite everyone to comments and ask questions throughout. That is to say, because the topic is somehow new or not necessarily as familiar as other element to some of us, feel free to interrupt and ask clarifications and questions in throughout so that we will all have. Okay? Very good.
Oh, sorry.
You want to start? Why don't we start? Please, why don't we start? No, I was just trying to negotiate this funny feeling of having somebody on my back, but I'm very happy for you to be the first.
All right, sure, thank you. My name is Vandi Kenyako. I'm a PhD candidate here at ICAR. And Andrea happens to be my committee chair.
Welcome.
I'm Manesh Failey-Atomba de Silva. I'm a PhD student at ICAR and one of the Cambi Fellows.
Welcome.
Hello, my name is Haruka Nakayama. I'm a master's student at ICAR, and I'm also his assistant.
Welcome. Behind the
sorry. I'm Molly Tepper, PhD student and Cambi Fellow, ICAR.
Good afternoon, my name is Tommy. I actually graduated a master's program at ICAR. I'm planning to go to Sudan next month to teach peace studies and conflict resolution.
Hi, my name is Tetsushi Ogata. I'm a PhD student at ICAR, and I'm assistant to Dr. Bartoli. I had a chance to listen to the DSD seminar last year, and I was intrigued by the theory idea, and I'm interested in this topic.
My name is Jason Miller. I'm a master's student here at ICAR, and I'm one of the program officers for Dr. Bartoli's EGVP program.
I'm Louise Diamond, and I'm not a student at ICAR. I guess I'm the only one. I don't know. President of the Global Systems Initiatives.
I am Jamil Mawad. I am with the International Negotiation Initiative at the Program on Negotiation at Harvard Law School. And I'm just visiting the university. We're teaching a class with Mark Thurston this weekend about leading from your spiritual center. And we were just trying to fix up the computers, and I learned about this, and I thought I have 15 minutes. I would like to have a taste of it, so that's why I'm here.
I will introduce Professor Leibovitch. I'm Andrea Bartoli, as I said, and I'm delighted that Larry is here. He's a scientist who started studying astrophysics and became interested in conflict through the interaction with Peter Coleman and two colleagues at Florida Atlantic University, Robin Valacher and Andrea Novak. So why don't you tell us a little bit more about this intellectual itinerary that brought you to conflict and conflict resolution studies and...
Okay. So my career path is a single line, but it just has many angles. It's not many lines. And as Andrea said, I was trained in physics and astronomy, and then I didn't like doing that anymore because I thought we made theories that we couldn't test. So I looked for other things to do, and I nearly became an insurance actuary, the people who figure out policies. But instead I got into doing biology, applied math to things in biology, and basically what I do now is I do things that are interesting. So when I see a problem that I think I can do something with, then I get involved with it. And the thing that unites all of the problems, I was actually going to give the trail, which I didn't do, which was from astronomy to understanding how sodium and potassium goes through cells, and they go through proteins, and then I studied the proteins, and proteins behaved in a certain way, so I did nonlinear dynamics, and then applied the nonlinear dynamics to other things. So that's the single line, and that's what I'll talk about today is dynamics. What unites all of the things that I do is I basically study systems that have many pieces where the pieces interact strongly with each other. And that pretty much characterizes pretty much all of the things that I do.
We're very happy that you're here. We are happy that, as I said, this is the beginning of a conversation, and Larry and I belong to this small group, this Dynamical System group with Larry, Robin Valacher and Andrea Novak at FAU, and Peter Coleman at Columbia University. So why don't you take it from here? Let's do the presentation and then...
Okay. Right, so let me give you the 4-sentence summary before you leave.
Thank you.
So the brief summary is, and this is the reason why both of us are really encouraging you to interrupt and ask questions, is my background is in the physical sciences and mathematics. The way we approach a problem is to look not so much at the simple pieces of the problem, but in essence, a stylized shadow of the problem. And then what we have from there, we can use the mathematics to absolutely predict what our assumptions lead to. In the social sciences, very often you try to paint a very beautiful, colorful, detailed picture, but then sometimes it's less clear where that takes you and how to determine where it's true. So in the physical sciences, we start off with a black and white, simpler picture, but we absolutely know from a couple of thousand years of mathematics how to pull out the absolutely logically necessary consequences of that. And what I'll show is the model we've been building of two people interacting with each other. And what are the consequences of some very simple assumptions of that model. So that's sort of the summary.
Perfect.
Yeah.
And this will turn on.
Shall we try turn it off?
Yeah, that will be good.
Yeah, that's fine.
We have enough light from the window already. We don't need
Yeah, this is fine. Yes. Start here a little bit. Okay, so this is, Andrea said, this is part of a group that's studying the dynamics of conflict at several different levels. at field studies, at social psychology experiments, and I and Andrea Novak are doing mathematical models. And so the people involved in this include Peter Coleman, who's originally organizational psych and does conflict resolution, Andrea here, who is trained in anthropology and does mediation, Andreas Novak, who does social psychology and mathematical modeling, Landry Brzezinska, who also does social psychology, and Robin Valek, who also at our place, who does social psychology. And what are dynamical systems are things whose variables change and evolve over time. And they can be lots of different types of variables. So they can be physical variables or biological variables. And today I'll talk about social variables. And what we're using is these dynamical systems to understand and resolve conflicts. And most of the people in the group use this as a metaphor, as a way of thinking about systems. Because thinking is hard. And actually, most of science consists of using analogies, although we talk about hypothesis and effects and things. But very often we reason by picking up something that we already know and using that as a description of something we don't know. But we can also use dynamical systems as a real mathematical model in a formal sense, and that's what I'll talk about today. So in terms of this is a metaphor, you basically say that if you have different variables, they all wind up in the same place no matter what you do. And we call this an attractor. And you can, one way to envision this is if this was a landscape with energy or with wells, hills and valleys. There are some hills out the window I can see. And nice cherry trees. I'm glad you arranged the timing of the cherry trees.
The spring is welcoming you, even though sometimes it's...
And so if you have a system where things roll downhill, they'll all wind up at the bottom, and that defines what an attractor is. And so the idea here, the attractors really represent the psychological, social, and cultural patterns that people display over times in a conflict, into which they return after temporary changes may occur. And no matter where people start, they still wind up on the attractor in an intractable conflict. But the attractors maybe can be changed, and so resolving a conflict can be done by shifting from one negative attractor to a more constructive attractor. So this is sort of the view of the group in terms of metaphors, although it's much richer than the simple description I just gave. But I want to talk to you about dynamical systems as mathematics. So what I'm going to be talking about is the interaction between two actors. So I never know whether I should call them actors or parties, whether we're talking about international relations or conflict resolution. But here they're being called actors. And so these two actors could be each a husband or a wife in a marriage, or each actor could be an entire cultural, political, or racial group, or maybe the two actors are two different nations. And what we're going to do is cast this model into equations. So this is the part that I think may be a little bit alien. So I'm going to talk a little bit explicitly about this. And if you have questions, please interrupt, because this is a little bit unusual. I find it's hard for me to understand anything the first time. I have to hear things about 3 times before I understand them. So please ask if something isn't clear. So the reason for doing this is actually...
I just wanted to double check on capturing what Larry said before about mathematics helping us to understand our own assumptions. Was that clear?
I thought actually he said mathematics helps us understand logical outcomes.
Yeah, that in a way helps us to understand how our assumptions can be logically be progressed, okay, and see what is the consequence of our thinking certain things. So it's a good tool. It doesn't say that reality is going to be that. It says simply that if this is what you are putting into the system, this is what you're getting out of the system. Okay, so it's a logic game.
All right, so as I was saying, reasoning in words can be difficult because sometimes different people can reach different conclusions. And so it's just hard. And so we encode these social mechanisms into equations. Oh, it's okay. We encode these social mechanisms. Stick with this. We can encode social mechanisms into these equations and then use the mathematics to determine the logically necessary consequences of these mechanisms. So it's interesting that this is what happened in physics. So before about 350 years ago, physical science used words as a language of science. And around the time of Isaac Newton, physical science started to use mathematics in order to describe the world. So why did this happen? And this shows the difference between approaching things maybe in psychology and in physics. So in psychology you have data and observations and intuition. This intuition part is actually important. And theory, and maybe from that you figure out a hypothesis, and typically you look for correlations between different variables in the system. Well, we don't do that in physics. In physics, we also start with the same data, observations, and intuition, but you just make stuff up. You just make it up, just like that. So, for example, Isaac Newton said that the gravitational force between two bodies would be proportional to the mass of the bodies and inversely proportional to the square of the distance between them. Now, there was nothing really to suggest why that should be the case, and he said that's the force between them. And by doing that, he was able to show with the mathematics to predict the orbits of the planets around the sun and their motion in the sky. He was able to predict the eclipses. He was able to predict tides on the Earth. So it led to really good, useful predictions. But it was not an explanation of anything. In fact, his theory at the time was heavily criticized as a return to medieval mysticism, because he didn't explain how this thing felt the force of the other thing. And in a famous statement in his book, the Principia, Newton wrote, non fingo hypotheses. I frame no hypotheses. He's not explaining how it works. In the social sciences, we use many words to explain how things work. And Newton said he's not going to explain it. He has this assumption, and he's going to see where the assumption goes. And if the assumption is good at understanding things, at understanding what we have, at predicting new things, then it was good to do. But he's not filling in the details. At the same time, the followers of René Descartes also had a model of gravity. And it was a wonderfully ornate, beautiful model. And they're wonderful woodcuts from this time period. And they said there are vortices in space. And each vortex pushes on the next vortex, and eventually a force is felt. And they had a wonderful picture of how things worked. But the best they could do was to predict that the Earth would be a little narrower at the equator. And Newton predicted the Earth would be a little fatter at the equator by about 0.3%. And when they measured it, the Earth was a little fatter. And so this wonderful picture where you could see how everything worked and all of it made sense, and there were words and there were pictures, fell by the wayside because the equations were better at predicting what happened. So what we do with these equations is, first of all, a qualitative prediction, like the fact that the Earth may be fatter or the tides. And this qualitative sense from the theory can be very important. So Newton could predict that the tide should be roughly at full moon, but they're not exactly. They're actually quite a bit off due to a couple of reasons. And so the qualitative prediction was also important. And sometimes we can do, a lot of times, quantitative predictions of particular values that we can compute in the theory and see if they're present or not present in reality. So actually what we're going to do here is I'm going to show you from the model we predict that people should behave in a certain way, and we're currently testing that with different social psychology experiments. So again, to try to make this difference clearer, Lewis Fry Richardson was a physicist, and in fact he was a Quaker and refused to participate in the First World War for the United Kingdom where he lived, and he drove an ambulance, and he was very interested in the causes of wars. And so after the First World War, he was making, trying to do a sociological approach of the areas of countries and their population and their wealth to see if he could identify certain causes of wars. And later on, he did mathematical models of how countries interacted with each other. And these were published in a book published about 6 years after he died by his students who put this all together. And in this book, he describes the advantages and disadvantages of using mathematics. And this looks like a bunch of quotes out of context, but this is actually a continuous quote directly from the book. And he says, to translate one's verbal statements into mathematical formula compels one carefully to scrutinize the ideas therein expressed. Next, the possession of formula makes it much easier to deduce the consequences. In this way, absurd implication, which might have passed unnoticed in a verbal statement, are brought clearly into view and stimulate one to amend the formula. An additional advantage of a mathematical mode of expression is its brevity, which greatly diminishes the labor of memorizing the idea expressed. Physicists think you should never memorize anything. You should have a few essential principles in you to derive things. They teach you not to memorize things. If the statements of an individual become the subject of a controversy, this definitiveness and brevity lead to a speeding up of discussions over disputable points, so that obscurities can be cleared away, errors refuted, and truth found and expressed more quickly than could have been done had a more cumbrous method of expression been pursued. And he also discusses the disadvantages of this. Mathematical expressions have their special tendency to pervert thought. The definitiveness may be spurious, existing in the equations, but not in the phenomena to be described. And the brevity may be due to the omission of the more important things, simply because they cannot be mathematized. Against these faults, we must constantly be on our guard. It will probably be impossible to avoid them entirely, and so they ought to be realized and admitted. So again, to what I said before, this is a model of shadows of people, but it has enough interesting features that the model does interesting things. And then we see whether people really do those things or not. So that's the approach here. And again, the goal is to understand what different social mechanisms do, to see if we encode them in the equations, do they really do what they think they do, or do they surprise us? And just to be clear, the goal is not to make a mathematical model of people or of conflicts that encompasses, describes, and predicts all of human behavior. The goal is to understand, when we make these assumptions, what are really the logically necessary consequences of those assumptions. So this work is based on work done by John Gottman, who's a psychologist, and James Murray, who's a mathematician, and their colleagues, where they made models of couples. And what they did is they interviewed 73 couples and videotaped them for 15 minutes, and every 6 seconds encoded their affect, and they used this as data to evaluate the parameters of a mathematical model that they derived. And that's enough about that. So this is what the model looks like. The variables x and y will be the current attitude of group X or group Y. And so this is really actor X or actor Y. These can be individual people or groups or nations. I'll usually refer to them as groups, because when I first did the slides, I used that word first, and I'm apparently now trapped into always using the word group. But they could be individual people as well. And we say that the attitudes of each group depend on their attitude at their previous moment in time and their natural inertia to change, their natural uninfluenced state when each group is separate from the other group, and the influence of each group on the other group. So these are what the equations look like, and I'll say in words what they mean. So what the equations say is that the rate of change of the attitude is proportional to 3 terms. The first term, which represents the inertia to change. The second term represents how they feel when they're alone. And the third term is the interaction between the 2 groups. And what form should we pick these influence functions of how one group influences the other? Well, actually, a number of people, including Richardson, have talked about types of influence functions which are really pretty similar. And I think it's best described by Morton Deutsch's comparing cooperation versus competition. And he writes, to put it colloquially, if you're positively linked with another, then you sink or swim together. And with negative linkage, if the other sinks, you swim, and if the other swims, you sink. So we pick functions that have this property. So that's illustrated by the graph here. So this is the attitude of one group, and this is the attitude of the other group. And this is a mathematical expression, but the only important part is whether the leading term is negative or positive. If that leading term is positive, each group tries to do the same as the opposite as the other group. So if this group is happy, it makes the other group happy. If one group is unhappy, it makes the other group unhappy. If this term is negative, each group tries to do the opposite of the other group. So if one group is happy, it makes the other one unhappy. And if one group is unhappy, it makes the other group happy. And we pick these particular functions because we want the groups to influence each other a little bit at low levels, so this is a proportional influence, but we want a threshold. So above a certain amount, no matter what the other group is doing, you just don't respond to it anymore. Actually, growing up in the Bronx, New York, my mother always said, if everyone else jumps off a cliff, are you going to jump off a cliff? And so that's this threshold. I don't really know why my mother said that, because in our part of the Bronx, there really weren't any cliffs. She's very focused on saying that. And so we have this function with a limit. And actually, quite a number of people, including Pruitt and quite a number of others, have, just as a figurative way, drawn S-shaped functions like this as a way of how people might interact. So this ties in to what other people's intuition are.
Dean sent his regards. He couldn't be here today, but he knew that you were coming, and he sent this.
Oh, thanks. So I'm not going to go through some of the mathematics that we can do with this, but I thought I would show you some of it so we have nice Greek letters and equations and symbols you don't understand, so that we can actually do some real mathematics on this. But rather than go through the mathematical analysis, I want to show you simulations of how people's attitudes would change in time under different circumstances, so you can get a feel for what the model is saying. And what I'm going to describe are cases where the 2 groups either try to do the same as the other group, the 2 groups try to do the opposite of the other group, or we have this mixed case. So what I'm going to show you here are simulations where we've plotted the attitude, that is the x or y variable, as a function of time. And if the influence between the 2 groups is small, for all 3 cases, in this case the 2 groups start off a little bit different from each other, but they both wind up to the 0 line, which means they're both neutral. Well, this alone is already something interesting from the mathematics. It says if the 2 groups don't interact, or do interact a little bit, you see no evidence of that interaction. That is, both groups wind up neutral as if they're not interacting, as if they have nothing to do with each other. So this is already sort of something interesting. There's not a proportional effect. So this is called a nonlinear system, which means things aren't proportional or simply related to each other. The relationships are more complex. And that's basically what I study, are nonlinear systems. So there's no proportional effect. It's as if there were no interaction between the groups. They both wind up neutral. Now let me show you what happens when the influence between the 2 groups is stronger. So we'll, I don't have the, oh, we missed something. This means I edited the previous presentation a little bit too much. Okay. So this I actually do want to show you, so I'm going to pull it up from another presentation. Like, do this one. This is what I'm looking for. This is the case where both people interact. So I changed the nomenclature to try to make it simpler and say